Chem 1212, welcome to the online demonstration of our first lab, which is enthalpy of vaporization. I am Dr. Roy Stansby Sparks. I'm going to be taking you through this lab demonstration today to give you an idea of what you would have been doing in the lab had you been doing yourself. Enthalpy of vaporization, or also heat of vaporization sometimes called, we're looking at how much energy is required to vaporize water from the liquid state to the gas state. And we're going to make some measurements of volumes at different temperatures in order to do that today. The first thing we need is the barometric pressure. So barometric pressure is atmospheric pressure, and it has to be collected on the day that you do the experiment. Today we looked it up. It's 30.2 inches, which translates to 767.1 millimeters of mercury. And that, if you convert it to atmospheres, again, 760 millimeters of mercury is 1 atmosphere, so we're just slightly above 1 atmosphere. That would be 1.01 atmospheres. Right, the first technique that we want today is to fill a graduated cylinder with a bubble of air and some water. So we're going to use a 10 mil graduated cylinder here, and we're going to fill it with deionized water. And the instructions say to fill it to approximately 7 or 8 milliliters. This is a pretty tall one, so I'm going to err on the side of caution here and go to about 8. And we also have a tall beaker here of deionized water, and we're going to invert this graduated cylinder into this water and hopefully trap this air bubble in here that's taking up the top about 1/4 of this graduated cylinder upside down inside the graduated cylinder. So we have to be fairly quick about this. And the idea is that we want about 4 milliliters of an air bubble in the end. And so actually I'm going to add a little bit more water here to make sure we're going to get about that. We can always add a little bit of air. Okay, so I'm going to invert quickly, dump in here. And it's too big, it's at 6, so I need to do that again and try to trap more water inside. Fill it up further. Okay. Now we're at 3. I'm going to actually try to get a little bit more air in here. Just gonna. Okay. Let's get a little bit bigger. Okay, we're right at about 4 now, so I think we're good. And now we're going to put this onto a heating plate and heat up the water until we get to about 80 degrees Celsius. Alright, so we have our graduated cylinder here inverted into our beaker, and our beaker is now warm. Our water is warm. We're at around 80 degrees, so that's good. And our bubble is almost at about 9 milliliters inside the graduated cylinder. So I'm going to take our first measurement here. And so I'm going to use this thermometer here, and our first measurement is going to be at 80.7 degrees Celsius, and we're going to read the volume in the graduated cylinder, and it looks like it is at nearly exactly 9, actually 9.0 milliliters. Okay, so now what we're going to do is we're going to cool this off and let this cool to another temperature and keep collecting data. So I have my data written here, and we'll just collect 7 data points between 80 and 50 degrees. It doesn't have to be exactly 50. We're just going to get data between that range, sort of. And then we'll show you how we get to the cold air at the end as well. Table, we'll call it a day. 66.4 degrees C, and the bubble is 7.6 milliliters. Okay, more ice. A little bit less this time. We can get 4 more measurements. There's still ice cube floating around in there? Or is it
That's the ice cube right there. I think it's gone now. Yeah, I believe the ice cube has been melted.
So next one, 63.4 or 63.8. 8 degrees C, and this is 7.123. Okay. More ice. Oh, that's too much, probably.
Well, you need more ice as you get further down.
True.
Oh, that looks like a perfect amount.
Actually, it did. It's like hotter up top than at the bottom here.
Yeah. Sounds like a dinner bell.
So 60.7 and 6.9. Last thing we need to do here is talk about what to do with our data. So we've collected our data now, and we have 7 temperature and volume measurements, and we have 1 temperature and volume measurement for the cold. We're going to separate the cold and treat it separately from the other 7. So the 7 hot measurements are what we're actually going to plot, and we're going to use the cold one to do a calculation. Okay, so if you remember back from Gen Chem 1, Chem 1211, we had the ideal gas law. So in the ideal gas law, we have pressure times volume equals number of moles times the gas constant times temperature. And so what we want to use that cold measurement for is to figure out the number of moles of dry air. So we're going to solve this for a number of moles of dry air, and that's going to be PV over RT. Okay, so we're going to use this as the cold temperature, cold temp, and we're going to use our volume from that 5 °C measurement. We're going to use our pressure as the barometric pressure that we talked about earlier, and we of course have our gas constant. That's going to give us the number of moles of just air inside that bubble. Again, the bubble when you heat is going to turn into air plus water vapor, and so we have to get this to be able to subtract it out to account for the amount of volume that's due to just air that we don't really care about in this experiment. Okay, so then we have our 7 temperature and volume measurements, and what we want to look at is vapor pressure. So we have to relate volume somehow to pressure, partial pressure of just the water. So when we go through the calculations, you're going to see that you're going to use the ideal gas law again, and you're also going to have to make a correction for the volume. So if you look at the graduated cylinder, we normally use a graduated cylinder upright, and so the tick marks that measure, or the graduated lines that measure the volume, are set up for a meniscus that's upright. But when we invert this thing upside down, the volume that we're reading is actually wrong because the meniscus is inverted, and we're looking at a bubble instead of a meniscus of a liquid, like normal. So you're also going to make a slight correction to these data points by subtracting a certain value from them to account for the flipping of the graduated cylinder. So you're going to have, in the end, a pressure and a temperature for each of these. And in this chapter's worth of material for Chem 1212, we talk about a relationship which is the Clapeyron equation. And the Clapeyron is a y equals mx plus b form, where we have ln of the vapor pressure is equal to negative delta H vat over R plus a constant. And a temperature, right? So here we have a y equals mx plus b form, where we're going to have a plot of ln of p on the y-axis, and we're going to separate this out so that we get delta H vat over R times 1 over t plus b, where this is slope here, and this is x. So we're going to plot ln of vapor pressure versus 1 over the temperature in Kelvin. Okay, you got to convert these to Kelvin as well in your calculations. That's going to give us a straight line plot. From that plot, you should be able to get the slope, and from that slope here, you should be able to calculate delta H vat. If you look back in the lab write-up, it gives you a table of delta H, or enthalpy of vaporization values for different substances. Water is on there, it's a known value. You should be able to get something that matches that fairly closely. So that should be your guide to having done these calculations correctly.